So for the second talk, for our second talk, we have the pleasure to hear Marine Le Morvan. She will talk about Neu Miss networks, differential programming for supervised learning with missing values. So Marine, the stage is yours.
Yes, well, thanks a lot for the invitation. So as Thomas said, I will talk about our recent work about Neu Miss networks. And this is joint work with Julie Josse, Thomas Moreau, Erwan Scornet, and Gaël Varocco. So in this paper, we talk about supervised learning with missing values, and in particular, linear regression with missing values. This problem may sound a bit easy at first sight, but actually, as you'll see, it is not. So to make the context a bit clear, in this paper, we assume that we have a response that is a linear model of some covariates xj, and a linear model of the complete data, so without missing values, which is in fact unavailable. And then our goal is to approximate a predictor that is the minimizer of the expected loss. So the optimal predictor is also called the Bayes predictor. And so what is difficult is that the minimization is on R union NA, which is the symbol for missing values. And so that makes the problem difficult because it means that you want to approximate a function that should be able to handle inputs of varying length, depending on how missing values you have in a sample. So in this work, we show that for certain missing data mechanisms, and that is going to be made clearer afterwards, the Bayes predictor is in fact linear per pattern. So it means that it is a linear function of the observed variables whose slopes depend on the missing data pattern. So to understand this intuitively, we can look at a very simple example with two covariates x1 and x2, and y is a linear model of x1 and x2. So on the figure you see y, the response, which is plotted against x1. And as you see, if we assume that x2 is missing, then it is still possible to partially account for its effect by adapting the slope of x1. So the dotted black line has a slope beta 1 star, which is the slope for x1 in the true underlying linear model. But as you see, it's not the best slope that you can choose for x1 to predict y. In fact, the best slope that you can choose is the orange one. And so this is only possible, of course, if x1 and x2 are correlated. But that means that, yes, by adapting the coefficient for the observed entries, you can compensate for the missingness of the missing ones. So that is for a problem in 2 dimensions, but when you are in d dimensions, there are 2 to the power d possible missing data patterns. And so the problem of approximating the Bayes predictor becomes much harder. Okay, so in this talk, we will try to approximate the Bayes predictor. And to do that, we will first derive its analytical expression under varying missing data mechanisms. And then we will introduce theoretically grounded neural network architecture that is designed to approximate the Bayes predictors. And finally, we'll show some empirical results. All right. So let's see what the Bayes predictors look like. But before, we need some notations. So X in this talk will be the complete data, which is unavailable. X tilde is going to be the incomplete data with NAs inside. And we'll denote by M the mask, also called the missingness indicator. It's a binary variable with D entries, where zeros indicates that an entry is observed and 1 indicates that it's missing. And so we will use ops M and miss M to refer to the subvectors that are observed or missing. So X ops is the subvector of X that is observed, for example. Okay. So let's start with the simplest missing data mechanisms. which is missing completely at random. And so here we provide the expression of the Bayes predictor under this missing data mechanism. So MCAR is mathematically an assumption that tells you that the probability of being missing doesn't depend on X. That tells you that the probability of being missing is just a coin flip of a coin. And it's the simplest one. And then you have missing at random, which is another usual missing data mechanism where you assume that the probability of being missing only depends on the observed entries of X. Okay? And so under these two assumptions, we can derive the expression of the Bayes predictor, which is given in the blue box. So as you can see, this Bayes predictor is linear per pattern, meaning it's a linear function with different slopes depending on the missing data pattern. And you can also see that it depends on beta star, mu, and sigma, which are unknown parameters. So to approximate the F star, you have a bit more work than just deriving its expression. So to give you a general idea of the proof, you have the 3 lines at the bottom of the slide. So the arguments that we use are the following. Since we have a squared loss, we know that the minimizer of the squared loss is the expectation of y given x, and in our case, x ops and the mask. Then we use the fact that we have a linear model, and so the expectation is linear. And so then we end up with the expectation of x miss given x ops and m. And because we have the assumption of MCAR or MAR, in fact, the expectation of x miss given x ops and m is independent of m. And finally, the expectation of x miss given x ops is known thanks to the fact that we assume that the data is Gaussian. And it's in fact the expression that is here in the Bayes predictor. Okay, so we'll now turn to a third missing data mechanism, which is self-masking. So this missing data mechanism is part of a missing not at random mechanism. So it's a notoriously difficult one, where the missingness is not ignorable. There's information in the missingness. And so more particularly here, we assume that the probability that a variable k is missing depend on xk through a Gaussian function with a certain mean mu k tilde and a certain variance sigma k square. Okay. And so under this assumption, we can again derive the expression of the Bayes predictor. So as you may see again, this expression is linear per pattern. That doesn't mean it's always true, but in this case it's true. And we highlighted in blue the parts that are similar with the MCAR and MAR cases. So just to highlight the fact that there is some similarity between these two Bayes predictors. Okay, so now that we have the expressions, analytical expressions of the Bayes predictor, we will try to approximate them. So here at the top, I just recall the expression for the MCAR case for simplicity. And so one first solution you can think of to approximate this is to use expectation maximization to estimate mu, beta, and sigma, and then use this estimate to compute the Bayes predictor. So this is possible, but it has several drawbacks. One is that this is not robust to the missing data mechanisms, since it would only be valid in the MCAR and MAR cases. And moreover, it has a high computational complexity. For more than a few dozen variables, it becomes intractable. Then at the other end of the spectrum, it has been shown lately that you can use a feed-forward neural network, which takes as input the data and the mask, with one hidden layer and 2 to the power d hidden units. And it has been shown that this neural network is consistent. However, it is largely overparameterized, meaning you'll need many samples to achieve a good accuracy. So with Neu Miss, we aim to be in between these two methods and provide the method which uses a restricted number of parameters by sharing the parameters across the missing data patterns and by keeping a computational complexity not too high. So here as d square. And so the key of the Neu Miss networks lies in the approximation of the sigma ops inverse that is highlighted in orange. So I will explain now how. Okay, so to approximate these inverses in a differentiable way, we rely on the Neumann series. So the Neumann series for sigma ops is written in this equation. And it's only valid if the spectral radius of sigma is strictly smaller than 1. But it's possible to go back to that case by just dividing sigma by a sufficiently large number. And then we approximate the sigma ops inverse by an orderal truncation of this series. So we just use L terms. And the orderal approximation of the series can be defined recursively by this second equation that is here. And so you can check that this is equal to the sum from k equals 0 to L of the thing. And in the end, the Neumann network is unrolling this iterative equation. Okay, so the Neumann network in the end approximate this function, which we call f star L, where we replace the sigma ops inverse by SL ops. Okay, and so to see how good is this approximation is, we provide an upper bound on its risk, which is given in this blue box. And the main thing that this upper bound shows is that if you increase the order L of the approximation, then your risk become closer to 0. Okay, so here is the Neu Miss architecture, which is depicted for a depth of 4. So you can recognize the Neumann iterations in the dashed block. So this block computes sigma ops inverse. Then one thing to note is that, in fact, if you choose the parameters of this network as the blue parameters, as the blue values, then this network will exactly compute the Bayes predictor. But in fact, since the sigma and the beta are unknown, then you cannot set these values like this. And then the other thing that I've not talked about yet is the non-linearities that we use. So they are depicted here as .m. So they are defined as the element-wise multiplication by the mask. So it's not a classical kind of non-linearity. And the reason why we use them is as follows. As you see in this equation, we repeatedly multiply by identity ops minus sigma ops. So in fact, we repeatedly multiply by a matrix whose rows and columns are zeroed according to the missing data pattern. And so one way to do this is to just to zero the good rows and columns, but it's not very efficient for batches of samples. So what you can also do is just mask the input and the output of this. So the input you give to the matrix for multiplication and its output. And so this is what is represented here. Instead of masking W1 new, we just mask its input and output. Okay, so yes, up to now we mostly talked about the MCOR and MNAR based predictors and how the Neu Miss network can represent it. But we have left aside the Gaussian self-masking case. And actually, with this slide, I'd like to show that the Neu Miss network may also be suited for the Gaussian self-masking case. So the first equation just recalls the MNAR based predictor. And in the second one, we recall the Gaussian self-masking one and the simplifying assumption, which is that this matrix D Miss, sigma Miss given ops inverse could be approximated by a diagonal matrix D hat. And under this simplifying assumption, if the network learns its parameters mu as the blue thing here, or its parameter W mix as the orange thing here, then it can exactly represent the base predictors in the MNAR case and in the Gaussian self-masking case. Of course, in the case where this simplifying assumption does not hold, then the Neu Miss network cannot exactly represent the base predictor in the Gaussian self-masking case, but it can still adjust its values learned for the parameters mu and W mix to approximate it. So to finish with the theoretical part, I will just show a last theoretical result, which gives a link between Neu Miss with a depth of 1 and a feed-forward layer, which will have as input x imputed by 0 on the mask and a ReLU activation function, and also d hidden units. So what we show is that, in fact, the weights of this feed-forward layer can be chosen so that the functions computed by its hidden units are exactly the same as the function computed by the hidden units of Neu Miss with a depth of 1. So what it says is that, in fact, a Neu Miss with a depth of 1 can be seen as a constrained version of the feed-forward layer. However, if we increase the depth of Neu Miss, then it can't be represented by the feed-forward layer. Okay, so I will now show some experimental results by applying Neu Miss to missing data. So this is the first experiment where we apply Neu Miss, a deep feed-forward network and a wide feed-forward network with one hidden layer to MNAR data with 50% of missing values. So here, as you see, if you increase the depth of the miss, it is much more efficient. Okay, I forgot to say here, the higher the better, with 0 meaning that the performance of your model is the same as the performance of the base predictor. So it's the best possible performance. And so you see that here, increasing the depth of the miss is much more efficient than increasing the depth of the deep or the wide feed-forward neural network. And so what that means is that the .m non-linearity is in fact crucial for the performance. And moreover, you can also see that when you have a depth of 1 for the feed-forward neural networks, you have almost the same performance as Neu Miss with a depth of 1, which is in line with the theoretical result we just saw. Okay, so this is just a simple experiment now which compares Neu Miss in green to what is called Neu Miss analytic. So this is in fact for the purple curve, we assume that we know mu, sigma, and beta, and we compute the base predictor where sigma ops is replaced by its approximation. So the purple line is basically the best FL star, it's FL star. And so as you see here, the Neu Miss, the weights learned by Neu Miss are such that its performance is better than the Neu Miss analytic. Okay, here we just show an idea of the number of samples required for Neu Miss to work well. So in this experiment, we run Neu Miss with a number of samples varying from 20,000 to 100,000 and dimensions from 10 to 50. And then we plot its performance against the number of parameters divided by the number of samples. And so as you see, Neu Miss works well as long as you have basically 10 samples per parameters. And so mathematically, its sample complexity is O of d squared because you have O of d squared parameters in Neu Miss. And to finish with, I show some performances of Neu Miss compared to some competitors on different simulations with different missing data mechanisms. So here in the simulations, we have a linear model with Gaussian data and a signal-to-noise ratio of 10. And we apply different missing data mechanisms. So either MNAR, MNAR, Gaussian self-masking, or probit self-masking. And then we compare expectation maximization, so EM, or imputation with MICE, which is a popular conditional imputation technique, followed by linear regression. Or the feed-forward neural network with one hidden layer and a number of hidden units varied between D and 100 times D, plus real non-linearities. And we give it as input the data imputed by 0 and the mask. And finally, we have Neu Miss with a depth varied between 0 and 10. And for both the feed-forward network and Neu Miss, we choose the width or the depth on the validation set. Okay, so here are the first results on MNAR data. So for the rows, you see that we increased the dimension from 10 to 50. And for the columns, we increased the number of samples from 20,000 to 100,000. So the first thing you may see here is that expectation maximization is the best performing method for a dimension up to 20. This is actually expected because EM is valid under missing completely at random setting. However, if we increase dimension to 50 here, EM was intractable. And after EM, then Neu Miss in green is the best performing method, except for the case D equal 50 and 20,000 samples, where actually Neu Miss is overfitting for a depth of 1. But by contrast, if you look at the case where we have at the top right, here you see that Neu Miss is almost reaching the performance of the Bayes predictor. Now these results are for the missing not at random case, Gaussian self-masking on the right and probit self-masking on the right, left and right. Here, EM, as you see, is no longer valid because we are in a missing not at random case. And so Neu Miss is the best performing method, still except for the lower left case. And moreover, you see that for the probit self-masking case, Neu Miss is still very good, although we do not have theoretical results for this case. So that means that it is quite robust to the missing data mechanism. Okay, so that is almost the end of my talk. So just to recap, we have presented a theoretically grounded architecture with a new type of nonlinearity and shown that it is robust to the missing data mechanism and suited for medium-sized data sets because it shares weights across missing data patterns. So thanks a lot for your attention, and if you have questions, I'm happy to answer them.
Thanks a lot, Marine. So if you have question, you're free to just like unmute your audio and ask them.
So maybe I can shoot the first question. So Alex speaking. Thank you very much, Marine, for the presentation. So it's more a question on the kind of opening. Probably people will have more technical questions on the paper on the presentation afterwards. But very often when you have missing data, it's coming from basically outliers in the data. So do you see a way of combining basically the dealing with the outliers and jointly with the missingness, in the sense that you can see outliers as therefore missing data? Do you see a way to combine these two standard learning problems, or have you thought about this issue?
I'm not sure I totally understand the question. You mean the outliers would be more likely to have missing values?
No, I mean, when you have an outlier, it's basically you have one feature which is just aberrant, or an outlier in the features, okay. And you say, okay, this feature is basically a typo in the input, and therefore I'm gonna consider it's missing. And so for you start with missing data, but very often sometimes when you have missing data, either it's the data was just not collected, or it was collected wrongly. And so you can end up in your missing data scenario because the data is just crap. And would there be a way to do the two at the same time, basically detect the outliers, and so it would be kind of two different statistical issues, detecting extreme values and also dealing with missing values. Have you thought about this?
Not really. Because the framework is really for prediction and handling missing values in this context. But what you say would be adding another layer where we would try to identify whether the value is missing or but actually, what you're saying could certainly be described as a certain missing data mechanism, I guess.
Yes.
So the idea would be maybe to try to write this missing data mechanism down and see if the current architecture readily handles it or not, theoretically and experimentally. But I have not thought about it more than that.
Okay. Thank you.
Thank you.